So the Bronsted-Lowery theory, to remind you, defines an acid as a species that donates a proton to a base. And the base, oppositely, is a species that accepts a proton from an acid. So it's all about movement of protons or H plus ions, right? Hydrogen ions. So species related by the addition or removal of a single proton are called conjugates in this theory. So when an acid gives away a proton in the acid-base reaction, what's formed is called the conjugate base. So the acid, once it gives away its proton, forms a conjugate base. And when a base gains a proton, the new species is called its conjugate acid. So in this case, we have a base and an acid, base here, and our acid here. And their products are going to be their conjugate forms. So let's look at our acid. Once it gives away its proton, which is here, it makes a conjugate base. And the base, once it gains a proton, forms the conjugate acid. Make sure you remember and are familiar with these terms of the acid and the base and the conjugate acid and the conjugate base. So you're going to need to be able to recognize where those are in the formula. I want you to also notice the curved arrows. We talked about curved arrows in the last lecture, and they're showing the flow of the electrons that changes the formal charges in this reaction. So I'm showing you this as a reminder that even though our proton is moving from the acid here to the base here, our electrons are actually moving in the opposite direction. You can see electrons are coming from the base to snatch that proton and then dissociating this bond here. We actually showed this almost exact example in our curved arrows example in the first lecture, dissociating this bond back onto the acid. And that's what forms these formal charges. So in the Bronsted-Lowery theory, we talk about the acid dissociation constant. This constant helps us talk about strength of acids. When water reacts with an acid, we know that it forms the H3O plus, and this is the conjugate base of the acid, A minus. So it dissociates into a proton, which reacts with the water to make H3O plus. This is the conjugate acid and the conjugate base, A minus. And the equilibrium for this whole process we define as Ka, this acid dissociation constant. So again, here we're showing the reaction. Here is the acid reacting with water. And notice the acid is donating its proton. That's what acids do, right? In a Bronsted-Lowery theory, acids donate their protons to the base, in this case, that is water. And they form, this is going to be the conjugate base of the acid, right? And the conjugate acid. Now the amount of conjugate acid, H3O plus, and conjugate base, A minus, that is formed, divided by the starting amount of acid we put in, gives us a Ka. So what this tells us is that if this number on the top is very big and this number on the bottom is very small, that's a situation where we put the acid in and most all of it dissociates. It gives away almost all of its proton and becomes the conjugate base and the conjugate acid. That is a situation where we have a strong acid. And so this top will be very big because we've dissociated our acid. And this bottom will be very small because the remaining original acid we put in has become all dissociated. So a big Ka ultimately means a strong acid. Now, if you have the opposite scenario, if you put an acid into water and it doesn't really do its job, it doesn't donate its proton, it doesn't dissociate, it stays as the original acid that you put into water, that means that your top will be small, right? You don't form that much product. And the bottom here will be big. So ultimately, our Ka will be small, and that means you have a weak acid. So that's how we get these numbers. But ultimately, remember that a large Ka is a strong acid and a small Ka is a weak acid. Now, it's important to understand Ka and where it comes from, but mostly we talk about Ka in terms of pKa. This is just the negative log form of Ka. And the reason we do this is just it's easier to talk about. The numbers are easier to deal with. They're numbers that are not fractions or less than 1. Instead, they're whole numbers, easier to work with. So when we convert Ka into pKa, it is the negative log. So that means that a very small pKa, so if we have a small pKa, that means also a big negative number, but a small number in general, that equals a strong acid. So it's the opposite rules. And a large pKa equals a weak acid. So remember, the rules are opposite. A large Ka is a strong acid, and a small pKa is a strong acid. So here's an example. If we just look at methane, CH4, its Ka is 10 to the negative 60. Whew. That is a very small number. 10 to the negative 60 is a very small number. It's, 0.00000, etc. And its pKa is 60. So Ka is small, pKa is big. That is a weak acid. For Hi here, we see its Ka is 10 to the 10. That's a very, very big number. So Ka is big. pKa, negative 10. Very small. Negative number. This is a strong acid. So again, just remember those rules for Ka and pKa and what they mean about the strength of the acid.